When dealing with multiple 120 volts linear load branch circuits originating from a 120/240 volt single-phase service, a question often arises about the grounded conductors and their termination. Specifically, can a single, larger grounded conductor be run to a junction box to serve these circuits, instead of running individual grounded conductors back to the panel? According to standard electrical practices and code interpretations, the answer is yes, with certain provisions. A single grounded conductor, sized appropriately, can indeed be run to the junction box to serve multiple branch circuits. In the described scenario involving 420 amps, 120 volts linear load branch circuits, it is permissible to run one conductor to the junction box sized at 40 amps. This approach implies a shared neutral configuration, also known as a multiwire branch circuit. The condition being that the ungrounded conductors are supplied by different phases. However, it is extremely important to ensure compliance with the National Electrical Code or NEC and local electrical codes. The NEC addresses multiwire branch circuits in Article 210.4. This section outlines the requirements for these circuits, including the need for a common neutral. A multiwire branch circuit, by definition, consists of two or more ungrounded conductors having a voltage between them, and a grounded conductor having equal voltage between it and each ungrounded conductor of the circuit, which is connected to the neutral or grounded conductor of the system. Multiwire branch circuits are commonly used to provide both 120 volts and 240 volts power from a single 3-wire cable consisting of 2 hot wires and 1 neutral. The advantage of a multiwire branch circuit lies in its efficient use of conductors. Instead of running a separate neutral conductor for each circuit, a single neutral conductor can serve multiple circuits, which reduces the amount of wiring needed and saves on material costs. For instance, in a typical 120/240 volt single-phase system, two 120 volt circuits can share a single neutral conductor, provided that the ungrounded conductors are connected to opposite phases of the service. The neutral conductor carries only the imbalance of the load. In the case of balanced loads, the current in the neutral conductor is minimal. However, it is vital to understand the implications of this configuration. Firstly, the grounded neutral conductor must be sized adequately to carry the maximum potential unbalanced load. Secondly, precautions must be taken to prevent overloading the neutral conductor if one of the ungrounded conductors is disconnected. In the context of the question regarding 420 amps, 120 volts branch circuits, the critical consideration is how these circuits are arranged across the available phases. If these 4 circuits are evenly split between the 2 phases of a 120/240 volt single-phase system, with 2 circuits on each phase, the neutral conductor only needs to carry the unbalanced load between the 2 phases. In a perfectly balanced scenario, the neutral conductor would carry no current. However, it is never safe to assume a perfectly balanced load. Therefore, the neutral conductor must be sized to handle the maximum possible unbalanced load. In the scenario, this is the equivalent of 220 amp circuits, which equates to 40 amps. Thus, the 40 amps rated neutral conductor mentioned in the question is appropriate, provided that the loads are reasonably balanced between the 2 phases. Furthermore, it is essential to ensure that the overcurrent protection device, such as a circuit breaker for each of the branch circuits, does not exceed the ampacity of the conductors. This is a fundamental requirement of the NEC and is intended to prevent overheating and potential fire hazards. Article 240.4 addresses the protection of conductors against overcurrent, specifying that conductors shall be protected in accordance with their ampacities. When using a shared neutral conductor, special attention must be given to maintaining the continuity of the neutral. If the neutral conductor is interrupted while the circuits are energized, the voltage on the 120 volt circuits can become unbalanced, potentially causing damage to equipment connected to these circuits. Therefore, it is imperative to ensure that the neutral conductor is securely connected and properly maintained. In addition to the NEC requirements, local electrical codes may have specific provisions regarding multi-wire branch circuits and shared neutral conductors. It is always recommended to consult with a qualified electrician or electrical inspector to ensure compliance with all applicable codes and regulations. The ampacity of the neutral conductor is another critical factor to consider. The ampacity of a conductor is its current carrying capacity, expressed in amps. The ampacity of a conductor depends on several factors, including its size, insulation type, and installation method. The NEC provides tables that list the ampacities of various conductors under different conditions. When sizing the neutral conductor for a multiwire branch circuit, it is essential to select a conductor with an ampacity that is sufficient to carry the maximum potential unbalanced load. In the case of 420 amps, 120-volt circuits, the neutral conductor should have an ampacity of at least 40 amps. However, it may be necessary to use a larger conductor if the loads are not evenly balanced between the phases or if other factors affect the ampacity of the conductor. The type of load connected to the branch circuits also influences the sizing of the neutral conductor. In the question, the loads are described as linear loads. Linear loads are those in which the current waveform is proportional to the voltage waveform, such as in incandescent lights and resistance heaters. In linear loads, the current in the neutral conductor is typically the arithmetic difference between the currents in the ungrounded conductors. However, nonlinear loads, such as electronic devices and LED lighting, can generate harmonic currents that flow in the neutral conductor. Harmonic currents can increase the current in the neutral conductor, potentially overloading it. Therefore, when nonlinear loads are present, it may be necessary to increase the size of the neutral conductor to accommodate the harmonic currents. The NEC provides guidance on sizing neutral conductors for nonlinear loads in Article 220.61. This section requires that the neutral conductor be sized to carry the maximum unbalanced load, plus an additional amount to account for harmonic current. The amount of additional current depends on the type and amount of nonlinear loads connected to the circuit. Another important consideration when using shared neutral conductors is the identification of the conductors. The NEC requires that all conductors be properly identified to ensure safe and reliable operation. The ungrounded conductors are typically identified by color coding or other markings. The grounded neutral conductor must be identified by a white or gray color. This allows electricians and other qualified personnel to easily distinguish between the ungrounded and grounded conductors. Additionally, the NEC requires that the neutral conductor be connected to the neutral terminal in the panel board. The neutral terminal is typically identified by a white or gray color. This ensures that the neutral conductor is properly grounded. The NEC also addresses the use of ground fault circuit interrupters or GFCIs on multiwire branch circuits. A GFCI is a device that protects against electrical shock by detecting ground faults. A ground fault occurs when current flows through an unintended path to ground, such as through a person's body. GFCIs are required in certain locations, such as bathrooms, kitchens, and outdoor areas, where the risk of electrical shock is higher. When using a multi-wire branch circuit, it is important to ensure that the GFCI is properly installed and wired. The NEC provides specific requirements for GFCIs on multi-wire branch circuits in Article 210.8. These requirements are intended to prevent nuisance stripping of the GFCI and to ensure that the GFCI provides adequate protection against electrical shock. In addition to the NEC requirements, local electrical codes may have additional requirements for multi-wire branch circuits and shared neutral conductors. It is always recommended to consult with a qualified electrician or electrical inspector to ensure compliance with all applicable codes and regulations. In conclusion, the use of a shared neutral conductor for multiple 120 volts branch circuits is permissible under certain conditions, as outlined in the NEC. The grounded conductor must be sized adequately to carry the maximum potential unbalanced load, and precautions must be taken to prevent overloading the neutral conductor if one of the ungrounded conductors is disconnected. It is also essential to ensure that the overcurrent protection devices for each of the branch circuits do not exceed the ampacity of the conductors. Furthermore, local electrical codes may have specific provisions regarding multi-wire branch circuits and shared neutral conductors. The appropriate size for the shared neutral conductor in the example described, involving 420 amps, 120 volts linear load branch circuits, is 40 amps, provided the loads are reasonably balanced between the two phases of the 120/240 volt single-phase service. Remember, safety is paramount when working with electricity. Always energize circuits before working on them, and follow all applicable codes and regulations. If you are unsure about any aspect of electrical wiring, it is best to consult with a qualified electrician. The NEC is a comprehensive document that provides detailed requirements for electrical installations. It is updated every 3 years to reflect changes in technology and best practices. It is essential for electricians, electrical inspectors, and other qualified personnel to stay up to date with the latest edition of the NEC. Many jurisdictions have adopted the NEC as their electrical code, while others have developed their own codes based on the NEC. Local electrical codes may have additional requirements that are not included in the NEC. Therefore, it is always important to consult with a qualified electrician or electrical inspector to ensure compliance with all applicable codes and regulations. Electrical work can be dangerous, and it is essential to take precautions to prevent electrical shock and other hazards. Always energize circuits before working on them, and use appropriate personal protective equipment such as insulated gloves and safety glasses. If you are not comfortable working with electricity, it is best to hire a qualified electrician. A qualified electrician has the knowledge and experience to perform electrical work safely and reliably. They can also ensure that the electrical installation complies with all applicable codes and regulations. When selecting an electrician, it is important to choose one who is licensed and insured. A licensed electrician has met the requirements of the licensing authority and has demonstrated competence in electrical work. An insured electrician has insurance coverage to protect against liability in case of accidents or injuries. It is also a good idea to check the electrician's references and read reviews online before hiring them. This can help you get a sense of their reputation and quality of work. In addition to hiring a qualified electrician, it is also important to maintain your electrical system properly. This includes inspecting your wiring, outlets, and switches regularly for signs of damage or wear. If you notice any problems, it is important to have them repaired promptly. It is also important to avoid overloading your circuits. Overloading a circuit can cause the wires to overheat, which can lead to a fire. To avoid overloading a circuit, do not plug too many appliances into the same outlet or use extension cords excessively. By following these safety tips, you can help to prevent electrical accidents and ensure the safe and reliable operation of your electrical system. The concept of voltage drop is important in electrical circuit design and installation. Voltage drop refers to the decrease in voltage that occurs along a conductor due to its resistance. All conductors have some resistance, and when current flows through a conductor, some of the voltage is lost due to this resistance. Excessive voltage drop can cause problems such as dimming lights, reduced motor performance, and malfunctioning electronic equipment. The NEC provides guidelines for acceptable voltage drop in branch circuits and feeders. In general, the voltage drop should not exceed 3% in branch circuits or 5% in feeders. To minimize voltage drop, it is important to use conductors of adequate size and to keep the length of the conductors as short as possible. The NEC provides tables that list the voltage drop per amp per foot for various conductor sizes and types. These tables can be used to calculate the voltage drop in a circuit and to select the appropriate conductor size. The ambient temperature can also affect the ampacity of a conductor. The ampacity of a conductor is typically rated at a certain ambient temperature, such as 30 degrees Celsius or 86 degrees Fahrenheit. If the ambient temperature is higher than the rated temperature, the ampacity of the conductor must be derated. Derating means reducing the ampacity of the conductor to account for the higher temperature. The NEC provides tables that list the derating factors for various ambient temperatures. It is important to derate conductors appropriately to prevent overheating and potential fire hazards. The type of insulation used on a conductor can also affect its ampacity. Different types of insulation have different temperature ratings. The temperature rating of the insulation indicates the maximum temperature at which the conductor can operate safely. The NEC provides tables that list the temperature ratings for various types of insulation. It is important to select conductors with insulation that is suitable for the operating temperature of the circuit. The number of conductors installed in a raceway or cable can also affect their ampacity. When multiple conductors are installed in a raceway or cable, the heat generated by the conductors can raise the temperature of the raceway or cable. This can reduce the ampacity of the conductors. The NEC provides tables that list the adjustment factors for various numbers of conductors in a raceway or cable. It is important to adjust the ampacity of conductors appropriately when multiple conductors are installed in a raceway or cable. The type of overcurrent protection device used in a circuit can also affect its performance. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors from overloads and short circuits. It is important to select overcurrent protection devices that are properly sized for the circuit. The NEC provides guidelines for selecting overcurrent protection devices in Article 240. It is important to choose overcurrent protection devices that will trip quickly enough to protect the conductors from damage, but not so quickly that they will cause nuisance tripping. Nuisance tripping occurs when the overcurrent protection device trips even though there is no overload or short circuit. Nuisance tripping can be caused by factors such as inrush current from motors or electronic equipment. The NEC also addresses the use of arc fault circuit interrupters or FSIs. An FSI is a device that protects against arc faults. An arc fault is an unintentional electrical discharge that can occur in damaged or deteriorated wiring. Arc faults can generate heat and can cause fires. FSIs are required in certain locations, such as bedrooms, where the risk of arc faults is higher. The NEC provides specific requirements for FSIs in Article 210.12. These requirements are intended to prevent fires caused by arc faults. In addition to the NEC requirements, local electrical codes may have additional requirements for overcurrent protection devices and FSIs. It is always recommended to consult with a qualified electrician or electrical inspector to ensure compliance with all applicable codes and regulations. Electrical safety is paramount when working with electricity. Always de-energize circuits before working on them, and follow all applicable codes and regulations. If you are unsure about any aspect of electrical wiring, it is best to consult with a qualified electrician. The information provided here is for general guidance only and should not be considered a substitute for professional advice. Always consult with a qualified electrician or electrical inspector before performing any electrical work. Remember, electricity is a powerful force and should be treated with respect. By following the safety guidelines and regulations, you can help to prevent electrical accidents and ensure the safe and reliable operation of your electrical system. The grounded conductor, often referred to as the neutral, plays a crucial role in electrical systems, particularly in alternating current or AC circuits. It provides a return path for current to flow back to the source, completing the electrical circuit. Without a properly functioning grounded conductor, electrical systems cannot operate safely and efficiently. The grounded conductor is typically connected to ground at the service entrance of a building, providing a reference point for voltage and helping to stabilize the electrical system. This grounding connection also helps to protect against electrical shock by providing a low impedance path for fault current to flow back to the source, tripping the overcurrent protection device and disconnecting the circuit. The size of the grounded conductor is determined by the size of the ungrounded conductors in the circuit. The NEC provides tables that list the minimum size of the grounded conductor based on the size of the ungrounded conductors. It is important to select a grounded conductor that is large enough to carry the maximum unbalanced load in the circuit. The unbalanced load is the difference between the current flowing in the ungrounded conductors and the current flowing in the grounded conductor. In a balanced circuit, the current flowing in ungrounded conductors is equal to the current flowing in the grounded conductor, and the unbalanced load is zero. However, in most circuits the loads are not perfectly balanced, and there is some unbalanced load. The grounded conductor must be sized to carry this unbalanced load. In addition to its role in carrying the unbalanced load, the grounded conductor also provides a path for fault current to flow back to the source in the event of a ground fault. A ground fault occurs when current flows through an unintended path to ground, such as through a person's body. The grounded conductor provides a low impedance path for this fault current to flow back to the source, tripping the overcurrent protection device and disconnecting the circuit. This helps to protect against electrical shock and prevent fires. The NEC requires that the grounded conductor be insulated in certain locations, such as in wet or damp locations. The insulation helps to protect the grounded conductor from corrosion and damage. The NEC also requires that the grounded conductor be identified by a white or grey color. This helps to distinguish the grounded conductor from the ungrounded conductors. The grounded conductor must be connected to the neutral terminal in the panel board. The neutral terminal is typically identified by a white or grey color. This ensures that the grounded conductor is properly grounded. The NEC also addresses the use of ground fault circuit interrupters or GFCIs on circuits that serve certain locations, such as bathrooms, kitchens, and outdoor areas. A GFCI is a device that protects against electrical shock by detecting ground faults. When a ground fault is detected, the GFCI quickly interrupts the circuit, preventing electrical shock. The NEC provides specific requirements for GFCIs in Article 210.8. These requirements are intended to provide adequate protection against electrical shock in locations where the risk of electrical shock is higher. In addition to the NEC requirements, local electrical codes may have additional requirements for grounded conductors and GFCIs. It is always recommended to consult with a qualified electrician or electrical inspector to ensure compliance with all applicable codes and regulations. Electrical safety is paramount when working with electricity. Always to energize circuits before working on them and follow all applicable codes and regulations. If you are unsure about any aspect of electrical wiring, it is best to consult with a qualified electrician. The National Electrical Code, or NEC, is a comprehensive set of standards and guidelines for the safe installation of electrical wiring and equipment in the United States. It is developed and published by the National Fire Protection Association, or NFPA, and is updated every 3 years to reflect changes in technology and best practices. The NEC is not a law itself, but it is widely adopted by state and local jurisdictions as the basis for their electrical codes. This means that compliance with the NEC is often legally required for electrical installations. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It provides detailed requirements for various types of electrical systems, such as residential, commercial, and industrial systems. The NEC is organized into chapters, articles, and sections. Each chapter covers a general topic, such as wiring methods or overcurrent protection. Each article covers a specific aspect of the topic, such as cable types or circuit breaker requirements. Each section provides detailed requirements for the specific aspect of the topic. The NEC is intended to be used by qualified electrical professionals such as electricians, electrical engineers, and electrical inspectors. It is a complex document that requires a thorough understanding of electrical principles and practices. The NEC is not intended to be used by homeowners or other unqualified individuals to perform electrical work. The electrical work can be dangerous, and it is essential to have the knowledge and skills to perform it safely. The NEC is constantly evolving to keep pace with changes in technology and best practices. The NFPA updates the NEC every 3 years to incorporate new requirements and to clarify existing requirements. The updated NEC is published as a new edition, and jurisdictions typically adopt the new edition within a few years of its publication. It is important for electrical professionals to stay up to date with the latest edition of the NEC to ensure that their electrical installations comply with the current requirements. The NEC is a valuable resource for ensuring the safe and reliable operation of electrical systems. By following the NEC guidelines, electrical professionals can help to prevent electrical accidents and protect people and property from electrical hazards.